So those of you that were away on Friday we started the first bit of this sheet here. We did the polling up on the screen there. We did questions 1 to 4. Sorry, 1 to 3. We did up on the screen, and then I had to do 4 to 8, which I'm going to hear some responses right away. And then it looks like I have a couple of clips to show you here. So we already talked about on Friday what 1, 2, and 3 were. What's a scientific model? What's a scientific law? What's a scientific theory? Really, all we did was I got your answers, but I didn't actually give you what I think they are, right? Okay, so that's fine. So what about number 4 here? How do we prove scientific theory? Let me just see if I can find the volunteer that wants to tell me. Connor, you usually got something to say.
I don't.
No?
No, you didn't look at me.
Well, you always have something to say, Connor.
I think Sean has an answer.
Yes, Sean has an answer. Sean, tell me, how do scientists prove scientific theories? It's not a hard question, particularly. Or maybe I should rephrase it. How do you think scientists prove theories? And I won't say right or wrong.
By making hypotheses and testing them.
Exactly. In other words, do an experiment, right? Doing an experiment. Connor. Doing an experiment. Good. All right. Let me see here. Who can I pick on?
Connor.
Sure. There's no right or wrong. There's no right or wrong answer here, Connor. So my question to you, Connor, is: do you believe in atoms? Do you believe that atoms exist? It's not a trick question, man. It's really. If I said to you, do you think aliens exist? Some people might laugh at you depending on your answer. But I don't think that anyone will laugh at you when you answer the question, do you believe in atoms?
Sure.
Why do you believe in atoms?
Oh my God.
Can anyone tell me why you believe in atoms? Lloyd, tell me. Do you believe in atoms?
Yeah.
Why?
Electricity works and causes waves and stuff.
Okay. Ever seen an atom before?
I have.
Yeah? Where did you see an atom? You're staring. You're looking at a lot of atoms right now, right? But you've never seen an individual atom. Lloyd is saying that he believes in atoms because things work. But would you not agree, sort of as a group, that maybe you believe in atoms because, well, we've been told all along that that's true, right? Maybe it's just one big scam we've been lying to you for all these years.
That's what makes sense.
I'm not going to answer that because there might be some believers in the room. Okay? But it's an interesting thought, right? You believe in atoms because you've been taught that all along. What if you've been taught all wrong right from the start? Now, believe it or not, that actually happened for quite a few years, right? Aristotle taught his students a lot of things, and he was completely wrong, and they never questioned him.
What did he say?
Well, he talked about his concepts about motion were wrong. He thought that a heavier object would fall faster than a lighter object. Like, you know how Galileo took the heavy cannonball and the light cannonball, the Leaning Tower of Pisa? He didn't actually do that, but that's the thinking, right? And then he dropped them, and Aristotle's followers would have said that, say it was twice as heavy, that it would have fallen twice as fast. It's not true. But people believed Aristotle for thousands and thousands of years. Okay? I'm not saying that we're lying to you about atoms. Atoms exist. Okay? We've got a lot of evidence, right? That's the word I was looking for, was how do we prove scientific theories? They do experiments and they collect evidence. Okay. Now, I talked to, what was the other classmate? Anybody want to share here how they think science and art are similar and or different? How are science and art, we'll go with the easy one, Mitchell, different? How are science class and art class different?
Well, art class, you're kind of drawing,
Yeah.
painting.
Yeah.
Science, you're like writing how things are happening.
Okay. If I gave you an assignment in an art class and gave you an assignment in a science class, what might be different in the way it's marked?
In art, there's no right or wrong answer. In science, there is.
Perfect. That's exactly the answer I was looking for. There's no, it's more of your opinion, right? Someone might say that's a lousy picture, but okay. Now, is there any similarities between science and art? And you got to think a little deeper for this one. I have a good answer, but I'm going to see if anyone else. Luke, science and art, how are they similar? Any ideas? Okay, that's pretty close. That's pretty good. See, things can be interpreted different. You might look at a picture and say that looks like junk, and some art critic might say, "What are you talking about? That's a masterpiece, right?" Would you agree that you got to know a little bit about art to truly appreciate good art? For the most part? Would you agree you got to know something about science to appreciate good science a little bit as well? Right? Like if I brought in some crazy wild-haired scientist and he started explaining something or other, then he could fill the whiteboard full of equations, you just go, I don't know what he's talking about. Right? You couldn't really appreciate it. Pardon me? You could appreciate the effort. I suppose that's true, right? But to truly appreciate what's going on, you have to have some understanding. Okay. And that question goes to what Luke was saying as well. Some scientists say the universe is expanding, some say it's shrinking, and others say that it remains a constant size or set. How can these scientists arrive at completely different conclusions when they're looking at exactly the same evidence? How can they come up with different conclusions looking at exactly the same results or evidence? It's human nature, by the way. Yeah, and they're looking for evidence that supports their point of view already. They have an idea in mind, and they look for evidence that proves that, right? And they could find exactly, or they could find their opinion justified by exactly the same evidence. All right. Can scientific theories change? Ben?
Yeah.
Can you give me an example?
No.
I bet you can if you think about it. How do you know scientific theories change?
You just prove it.
I might be lying, remember.
You just said something about Aristotle and how the things fall.
True enough, yeah. Think about the solar system. Now, that's not really a theory, it's more of a model, right? But tell me how the model of the solar system has changed over the years.
Pluto was knocked out.
That's true. Pluto is now booted out. Think about a change that happened like 400 or 500 years ago. What did they think was at the center of the solar system before? Earth. And now, of course, we know that's not true, right? Theory of, you guys know about Pangea and continental plates and all that stuff, right? If you could actually find an old textbook from about the 1920s, none of that would be mentioned. Okay, it was only about the 1940s, 50s that idea of continental plates and shifting actually came true, or came to light. Okay, so theories do change over time. Climate change theory, is that a changing theory as we're going forward here? Yes, very much so. Very much so and very much current.
What's the other one?
My pleasure. So the question on the board is, and I'm just going to do this. Maybe I'll just write it here. I probably should have it here. The question on the board is hypothesis, and I spelled that wrong, theory, and I spelled that wrong, law, and I spelled that wrong. Excellent. Might as well make it, you know. What did he say about hypothesis, theory, law? He said rubbish. He said rubbish. Now, how many people, when you walked into class today, believed that you made a hypothesis, you did some experiments, you came up with a theory, and then if you did enough experiments, it became a law? How many people honestly thought that was true? I'm guessing all of you. You're all wrong. You're all wrong. Okay? The thinking or the quotation, it's just a theory, is really wrong. Okay? How about, you know what, can I meet you guys at deal?
Yeah.
Because I know that.
No.
All right. So, Connor, I'm going to take that away and you won't get to 10 minutes. Hypothesis, theory, law, true or false? Completely false. Rubbish. Theories are not unproven laws. Theories are not unproven laws. In fact, that is, if you get anything out of today's little discussion, you need to know that. Theories are not unproven laws. Let's have a look at this one here, climate change. What did he say right at the very end? It's just a scientific theory.
Took the television world by storm.
My dog makes me holler when it boo boo.
If you thought she was crazy, meet her family.
He said it's just a scientific theory. Obviously, he wasn't paying attention in grade 11 physics class. Science teachers throughout America are cringing as they hear that. What does it mean when you say it's just a scientific theory? What does it mean? It means you believe that theories are unproven laws. Can you prove a theory? Not 100%. There will always be a chance that the next time, this might be the time. Nope, came down. But that's because it's not a theory. The theory of gravity, it's just an expression. It's the law of gravity. The law of gravity says, because every time I throw the tennis ball up, it's the law. And that's one law you do not break. Yeah, well, but that's, you know what? Some laws, as they all say, some laws are made to be broken, right? There might be someday, but it's not. Okay? I suppose, yeah. Yeah. There's always an exception, right? Lloyd's right. If I throw it high enough, it would not come down. You're absolutely right. So I want you to understand here, lots of people think that you make a hypothesis, and you develop a theory, and then eventually you prove it. Not true. Not true. Governor Rick Perry, you're wrong. He has a little more power than me. All right. Okay. All right, so flip to the next one there. You'll notice that there's a cartoon of Einstein, and you probably can't read it, but he's got E equals ma squared, he's got that scratched out, and he's got E equals mb squared, he's got that scratched out, and it says theories are not really developed that way. Like, they don't just guess, right? What is that equation? E equals mc squared. Little joke there. What does E equals mc squared mean? Excellent question. E stands for energy. Yeah. M stands for mass, and c squared stands for the speed of light, which is 3 times 10 to the 8 meters per second squared. It talks about the amount of energy that exists in a mass. That's why you can get so much energy out of nuclear energy, right? Because you don't need much mass because the speed of light is so big. It's a complicated law. It's famous, but nobody ever really understands. Not the average person. All right, let's talk about models, theories, and laws here. So it says, and you might want to have a highlighter with you, or a pencil, or whatever. When scientists are trying to understand a particular set of phenomena, what's phenomena? Not a word, not a song they sing on Sesame Street. Not that one. Okay? Phenomena are just things that we observe. They often make use of a model. A model in the science sense is a kind of analogy or mental image of the phenomena in terms of something we are familiar with. There's a definition of a scientific model for it. Okay? It's a kind of analogy or mental image of the phenomena in terms of something we are familiar with. It's a way to describe something. One example is the wave model of light. We cannot see waves of light as we can water waves, but it's valuable to think of light as if it were made up of waves because experiments on light indicate that it behaves in many respects as water waves do. So we can talk about waves of light as a model. Okay? It's called the wave particle theory. Theory. The purpose of a model is to give us a mental or visual picture, something to hold on to when we cannot actually see what's happening. Models often give us deeper understanding. The analogy to a known system, for instance, water waves in the above example, can suggest new experiments to perform and can provide ideas about what other related phenomena might occur. No model is ever perfect, and scientists are constantly trying to refine their models or to think up new ones when old ones do not seem adequate. Okay? And the classic example of this, Connor, is the atomic model of matter. Well, I can see you're not listening. You're sitting there talking to Ben, you're smiling, you're laughing, and none of this is funny. Alex. None of this is funny. Right? So come on. The atomic model of matter has gone through many refinements. At one time or another, atoms were imagined to be tiny spheres with hooks on them to explain chemical bonding. They thought atoms were like tennis balls made out of metal, and that there was little tiny hooks on them, they hooked together, and that's what caused them to stay together. What else are they going to think 400 or 500 years ago, right? Okay, we didn't have Velcro. Okay, or as tiny billiard balls continually bouncing against each other. More recently, the planetary model of the atom visualized the atom as a nucleus with electrons revolving around it, just like you've seen in grade 9 science. You know, you got your nucleus, right? And you got your electrons whizzing around outside. That's what you guys believe, right? Yeah. Not so much. So more recently, the planetary model of the atom visualized the atom as a nucleus with electrons revolving around it, just as the planets revolve about the sun. Yet this model, too, is oversimplified and fails crucial tests. Why do we teach it in grade 9 science? It's simple. It's good enough. It's all a grade 9 student needs to know, but as you go on in chemistry, you're going to need to have a deeper understanding. And so we refine that model.
Do you get along with Mr. Friesen?
Get along just fine.
Is it competitive with you two?
Yeah, we have weekly races. You may wonder what the difference is between a theory and a model. Sometimes the words are used interchangeably. Usually, however, a model is fairly simple and provides a structural similarity to the phenomena being studied, whereas a theory is broader, more detailed, and attempts to solve a set of problems, often with mathematical precision. Often, as the model is developed and modified and corresponds more closely to experiment over a wide range of phenomena, it may come to be referred to as a theory. The atomic theory is an example, as is the wave theory of light. So it can happen. What they're saying is that models over time, I spelled models wrong. What's my spelling today? Models can become theories. Because theories are big sort of concepts, like they fill books kind of, right? And if you have enough sort of notes with your model, well then it's kind of like a theory. Okay? If you put enough words in your short story, well eventually it becomes a novel. Kind of thing. Models can be very helpful and they often lead to important theories, but it's important not to confuse a model or theory with the real system or the phenomena themselves. Now, here's what you do need to know. Scientists give the title law to certain concise but general statements about how nature performs. For example, momentum is conserved. That's known as the law of conservation of momentum. Another law that you might be familiar with is the law of conservation of, starts with E, or M, mass. Right? You know that one, right? Those are laws because matter must be conserved. End of law. No, doesn't need to fill a book. Matter must be conserved. Period. Sometimes the statement takes the form of a relationship or equation between quantities, such as Einstein's famous equation E equals mc squared. A better example for you might be Newton's law, which says F equals ma. Right? Those are laws. Those are things that we always observe. They are true. When the ball goes up, the ball comes down. Law of gravity. Okay? It's not like, you know what? I'm thinking if I throw this ball up, it might come down. That's my theory. Oh, now it's a law.
So what if you threw it against the ceiling and it fell ball?
Well, there's always exceptions, aren't there? To be called a law, a statement must be found experimentally valid over a wide range of observed phenomena. Otherwise, you have to have done it several times. In a sense, the law brings unity to many observations. For less general statements, the term principle is often used, such as Archimedes' principle. So a principle is like a law, but a really specific kind of law. In this particular situation, this is what happens. Where to draw the line between laws and principles is, of course, arbitrary, and there is not always complete consistency. Let me give you an example. If it's not a tennis ball, if it's a pink ruler, I could say the principle of pink rulers is that if I throw it up, it will come down. The principle of red click pencils is that if I throw it up, it must come down. Okay, eventually, if you do it enough, you can say, oh, we can develop a law, right? That's a little bit more generalized. Scientific laws are different from political laws in that the latter are prescriptive. What is that? You guys know what former and latter means? What does ladder mean? And not the thing that fireman class. The last one. And there's two, right? The latter is the second one, and the former is the first one. So it says scientific laws are different from political laws, and that the latter, the political ones, are prescriptive. They tell us how we must behave. You got your driver's license, right? Listen. Okay. Well, when you come to a stop sign, what do?
Stop.
How come?
It's a law.
It's the law. What happens if you don't? Does the universe get ripped apart?
No.
You just get a ticket. Right?
Yeah.
That kind of law tells you how you should behave. Tennis ball, you should come down. He listened to me. But if I make a law that says tennis balls must stay up, no, they don't listen. Okay, so that's the difference, right? Prescriptive law, they say how you should behave. Descriptive law, that's scientific laws. They tell you how nature should, or they do not say how nature should behave. They tell you how it will. Okay? Flip the page. As with theories, laws cannot be tested in the infinite variety of cases possible. Okay? You cannot spend your entire life, well, you could, throwing things up in the air, trying to disprove that law. It would be a waste of your life. So we cannot be sure that any law is absolutely true. We use the term law when its validity has been tested over a wide range of cases and when any limitations and the range of validity are clearly understood. Even then, as new information comes in, certain laws may have to be modified or discarded. Scientists normally do their work as if the accepted laws and theories were true, but they are obliged to keep an open mind in case new information should alter the validity of any given law. So they sort of are constantly trying to refine that, and if something comes up, oh, hang on, we got to fix this, right? Then they make a minor modification. I'm going to leave those questions for a bit. I'm going to flip to the last one, okay? Because I really haven't told you what a theory is, and I need to go through this. And I know this isn't the most exciting thing. Science is more than just a collection of facts and observations. Models, laws, theories, and evidence all play an important role in understanding the nature of science. A scientific model is, and now here's a really good definition. Highlight this one. A scientific model is a conceptual representation or idea in your head that stands for and helps explain other things, like the Bohr model. Is a good example. A model can be physical, a real thing like the globe, can be imagined in your brain like the Bohr model, or mathematical like numbers and formulas. In science, we develop models that have explanatory and predictive powers, like the model of the universe, and we test these models in the world around us. If our model predicts our observations, we accept the model as a valid description of our world. However, if our model encounters discrepant events, anybody ever heard that word discrepant? What's a discrepancy? Nick, what's a discrepancy, do you know?
Is it different? You know, the difference.
Did I spell that right?
No.
I just made a discrepancy.
Yeah.
I did it on purpose, by the way, because I knew that it was wrong. That's a discrepancy. When I encounter an error, what do? Fix it. Same idea. When you discover a discrepancy, a discrepant event, then we fail to provide adequate explanations. We begin to modify our model or search for an entirely different model. We fix it. A good example of a scientific model is the model of the solar system. At one time, it was thought that the sun revolved around the Earth, and this geocentric model of the universe was considered to be a true representation for many centuries, because they really couldn't go in spaceships and go figure it out, right? The model encountered a discrepant event when the retrograde motion of the planets did not exactly fit the epicycles of the geocentric model. Suddenly, I slipped into Chinese there. What the heck is that all about? Anybody know what retrograde motion is? Turns out if you happen to be an astronomer, and you might know this in grade 9 astronomy, I know Mr. Friesen teaches that, you notice how the planets go through the night sky, right? Well, it turns out that sometimes they sort of loop back on themselves. That's called retrograde motion. Okay? You would expect it to just sort of go across the sky from night to night, but it turns out there's times when it loops back. And so they noticed this retrograde motion, and it did not fit the epicycles of the geocentric model. In other words, they couldn't use the Earth at the center. They couldn't come up with a way to explain that. It was a mistake. How do we fix it? Well, Copernicus said, let's put what at the center? The sun. Let's put the sun out, and let's make it work that way. Oh, hey, this makes a lot of sense. A new model, the Copernican sun-centered model, provided a simple explanation of the movement of the planet, and it predicted the phases on Venus. You know how the moon goes from like quarter moon, half moon, three-quarter moon, full moon? Venus does the same thing. You just can't see it because it's so far away. The geocentric model couldn't do it. You throw the sun at the center, the heliocentric model, and suddenly things make sense. Oh, this is good. Years later, the invention of the telescope permitted more sophisticated observations to confirm the predictions of the sun-centered model. All right. I promise I'm going to try to wrap up real quick because I know this is boring. Observations can be used to test models, both externally or by thought experiments, as we rethink and apply our model to new and sometimes destructive situations. Our observations can lead us to identify regularities and patterns in nature. Why did I just raise my voice there? Was it because I was angry at this? Regularities and patterns in nature. We call these regularities and patterns scientific laws. For example, a simple scientific law would be what goes up must come down. We can also deduce laws given a certain set of conditions. For example, if light is a wave, we can geometrically show that the ratio of the sides of the angles of incidence and refraction is a constant. Or Chinese. That's known as Snell's law, by the way. We can often represent laws in mathematical relationships like Snell's law, Ohm's law, Charles' law, or Newton's laws. If only there was a law named after me. Contrary to popular belief, laws are not absolute and are often constrained to certain conditions. Ohm's law is valid only for some materials, and our pressure law is constrained by temperature. Even Newton's laws are valid only in inertial frames of reference, and I'm not going to get into that. But Newton's laws aren't true throughout the universe. They depend on the situation. Scientific theories form explanatory systems for phenomena and their corresponding laws and may include presuppositions, models, facts, and laws. What's a presupposition? More big words today. You might want to take a guess at presupposition. If I said assumption, would you know what an assumption is? Yes, so a presupposition is like an assumption, something that you already assume. Okay, so scientific laws or theories are big, giant things. They work on assumptions, and there's models, and there's math, and there's facts, all kinds of things. For example, Einstein's theories presuppose that the speed of light is constant in all frames of reference. Einstein's theories are based on that the speed of light must remain the same. If that's not true, then Einstein's theories fall apart. Okay, so that's a presupposition, an assumption. In Einstein's world, Newton's laws, such as F equals ma, hold only for objects that are moving much more slowly than the speed of light. F equals ma doesn't work at the speed of light. We must be very careful how we use the term theory, and that's what I'm getting at here with these videos. In everyday usage, the word theory often refers to an idea that is not proven. Walking down the street, if you say, yeah, it's just a theory, yeah, that's sort of what our everyday language says, right? But if you're talking about scientific theories and you're running for president, you better know what you're talking about. It's partially true that some theories, like many cosmological theories, are speculative ideas. What does speculative mean? You're speculating on the stock market. What does that mean? You're guessing. You're hoping. You're guessing. And are based on little evidence. Additionally, children often hold simple or naive theories about why things float or why the sky is blue. Hypotheses or proposed solutions are also often speculative, and we often seek to build support for them through predictions and observations. However, other theories, like theories of radiation, metabolism, or chemical bonding, have considerable evidential support. In other words, we got lots of evidence to back them up. It's impossible to prove our theories for every possible case. Are we going to prove that global warming, climate change is man-made? No, because you're not going to convince every single person. It's not going to happen, okay? You are never going to prove a theory. But you do need to know this, that there are different kinds of theories. And I would like you to just jot this down at the bottom there where there's space. There are types of theories, and they are speculative, and they range to what we call robust. Types of theories, speculative and robust. And they are on what we call a spectrum, a scale. What's it like out today? It's cool, it's hot, it's cold, all sort of relative, right? And when it's kind of between cool and hot, it's kind of, right? It's a spectrum kind of thing, okay? Most theories start out as speculative. When I say speculative, that usually means a guess, little evidence. Little evidence, very little evidence. You know what? I've got this theory about something or other, and I'm going to try it out. I don't have too much evidence yet, but I'm going to give it a whirl. And as I do more and more and more experiments, my theory becomes more and more robust because now I have more evidence. And I might have convinced a few other people to join me. I'll get you in a second on that, right? And once the scientific community says, yeah, you know what, Bennett, you're right on there. We believe you. I've done those experiments myself, and I got exactly the same thing. That is a robust theory. Go ahead.
So you said, if you say it's just a theory, then you're wrong. But if you just said it's just a speculative theory, would that be?
That would be correct. It's just speculation. Now, slide into the topic of climate change. Is climate change a speculative theory?
Yeah.
Some people would argue yes, right? It certainly started out here. Is there evidence for man-made climate change?
Yes.
There is. Some people aren't believing it, right? There is. Is climate change becoming robust? Yes, there's still some people that are considering it speculative, right? Some of those people have business interests. That gentleman there, right, running for president, probably a lot of money in his pocket because of big businesses that don't want it to become robust. Lots of scientists would disagree with you, and I'm trying not to be too political. All right, so anyways. However, other theories like theories of radiation, metabolism, or chemical bonding have considerable evidential support. So in other words, there's lots of evidence. It's impossible to prove our theories in every possible case, but robust theories explain a great deal, and we sometimes literally bet our lives on them. Right? You think about all the safety measures in cars and whatnot. We're betting our lives on them. Therefore, scientific theories lie along a spectrum from speculative hypothesis to robust explanatory systems. In science education, we often use early models and theories that are adequate for a less sophisticated understanding of a scientific concept. For example, Bohr's model of the atom, if you aren't flipping the page, it should be. Bohr's model of the atom explains all the phenomena one might examine in an introductory chemistry program. More progressive theories require a more extensive background. While it's important that our understanding of the nature of science is embedded in the context of the world of rational can be understood, we can never really know if we've achieved the most rational explanation. In science, the truth is elusive, just like the X-Files. But our beliefs must extend far beyond individual opinions. In science, we insist on an evidential argument. In other words, show me the evidence, show me the proof, show me the money. Show me the money, okay? I will leave the last bit off because I can see that I've lost you on a good part, okay? But know that, please, at the end of today, laws are not proven theories. Okay, there's no such thing as a proven theory. There are only robust theories.